Okay, well, welcome everybody to the Geoimage webinar on spectral analysis applied to mineral exploration. And my name is Mark Covington, and I'm the CEO of Geoimage. I'm passionate about remote sensing, and I started my career about 3 decades ago as a young geophysicist. My career progressed from exploration through mining, later into software development, but always focused on exploration and mining, project management, research, until I arrived here at Geoimage about 8 years ago. So again, welcome. And I'll just go through the agenda for us this afternoon. So the welcome is done, I think, pretty much on time, which is a good start. I'm going to talk a little bit about Geoimage, and then I'm going to hand to Rocio, who's sitting right next to me, and she's going to give us the good oil on mineral exploration using satellite imagery. I'll follow up with a few minutes after Rocio has finished to talk about some of the, I guess, the challenges facing hyperspectral and its application to mineral exploration in the future. I'm going to hand over to my colleague Essex from Account Management. He will give us a few updates on services and products. Thanks, Essex. We'll have a Q&A, and there's the final wrap up. Okay, so the purpose of this webinar, Geoimage does a lot of different things across the satellite spectrum, but we thought in particular hyperspectral, multispectral, and the application of that technology to mineral exploration was something close to our hearts. So we thought we'd put it out there to see who else would be interested, and judging by the number of registrations, we were quite pleased. So basically we want to ask a few questions, and Rocio is here to answer those questions. So we basically, how can we use satellite imagery to detect and map minerals on the Earth's surface? So that's the first question. Second one, how can we use satellite-based exploration to support fieldwork planning? Thirdly, how do you choose the right satellite technology? So there's quite a number of satellite technologies out there. It could be a bit overwhelming if you're not sure, what you're looking for. And it really comes down to understanding your own needs in terms of resolution and in terms of the actual spectra that you need to identify the minerals that you're actually looking for. A little bit about Geoimage. So it started in the 20th century in Mount Isa mines up in northwest Queensland, where coincidentally I actually did work as a junior geophysicist many moons ago. So it's kind of ironic that I come back to a company that was, I guess, forged in that part of the world. We have a few key sectors that we service from our base here in Brisbane. There's the government sector. Primarily, we will do whole of state captures using technologies such as the Airbus Spot 6 1.5 meter ground resolution, and that is used to capture very large areas in a fairly short period of time. So, for example, the whole state of New South Wales, we can capture in about 2.5 to 3 months. Mining, of course, I won't dwell on that because that's what we're here for. The environment, there's a lot of work in the environment, deforestation, looking for illegal earthworks, for, I guess, deflecting natural water courses. Carbon accounting, of course, is quite an interesting topic as well. And then there's infrastructure, and infrastructure in particular, we are using the INSAR technology to look at very minute changes in surfaces. So that's a quick rundown in terms of which sectors we service. In terms of mining and exploration, we have quite a broad suite of products and services that we offer. As I said, we started in Mount Isa, so Geoimage was born out of the ground, so to speak, by our two co-founders. And now we've progressed over the last 3.5 decades. We specialize in very, very high imagery. And what we mean by that is 15 centimeters if you include super resolution, and that's probably a topic maybe for another webinar, but 30 centimeters native, which is the highest commercially available satellite imagery, to around about 1.5 meters. Of course, there are plenty of satellites that give you broader or coarser resolution, but in general, Geoimage, we specialize in that very high resolution range. We've developed our own in-house change detection specific for the mining sector using AI. We do use in-soil monitoring for tailings dams, and as the slide says there, with an accuracy to 1 millimeter. And of course, explore for critical minerals using our Spectral suite. We can also measure stockpiles through the use of tri-stereo data, which gives us very good vertical resolutions. And yeah, there's plenty of other sort of services too. But let's get on to the main game, the main act. And before I do that, I'll just introduce some of our partners. So we do have access to over 60 satellites that we've partnered with from companies around the world. So there's a few of them there. Just a quick shout out to Vantor, formerly known as Maxar, but just rebranded in the last few days. So you'll probably see in this logo and this name crop up in lots of different places. We have a multidisciplinary team that we've grown over the years. So I just wanted to touch briefly on that. There we all are on the moon, holding something high. I'm not sure what that is. ChatGPT sort of helped me with this image, which was great. Actually, didn't come out too badly. So just quickly, we've got machine learning skills in-house. We've got specialists with environmental knowledge, obviously specialized team of individuals that do the pre-processing or the satellite imagery for us, geological knowledge in Rossio and myself, spatial data analysis, and also software engineering. So we do develop our own services in-house. And now I'd like to introduce Rossio. So Rossio has only been with Geoimage for a short time, probably about 4 months. Yeah, 4 months. But she's very talented. I have to say, she's probably a little bit modest as well, but she's very talented. She's very intelligent. She's got a range of experience. She started life as an exploration geologist with geochemical background. She's worked at a few different companies in different countries. So across the Americas, Australia, and Europe. She has a great knowledge of ore body, particularly with copper porphyry systems. And and a deep knowledge of hyperspectral. She actually graduated with a PhD from the University of Queensland back in 2022, and her expertise is actually in applying spectral analysis to mineralogy. So we're in good hands this afternoon, and I'll just hand it over to Rossio.
Thank you, everyone, and thanks, Mark, for the introduction. And I'm glad to see so many people joining us today. So yeah, I'm gonna talk today about how we use mineral exploration, satellite imagery for image exploration. So this is basically a webinar trying to respond some of the basic questions that geologists have, or maybe GIS specialists, when we think on different options that we have to put some layers about the spectral mineralogy for mineral exploration. So I wanted to start by talking about spectral mineralogy in the mining value chain. So we have that spectral mineralogy can be applied at different stages. So from exploration, mining, processing as well, and monitoring and remediation. So it is all based on looking at the response of minerals on the ground. And we use different sensors. And those sensors are the one that you can see on the right side of my slide. We have all those sensors that we use for remote sensing, on satellite, airborne, and drone-mounted cameras. We also have field spectrometers, and we also have core scanners. So all those different sensors apply at different resolutions, and they are designed for different applications, but they are all based on the same principles. So the first question is, how can we use satellite technology to detect and map minerals on the Earth's surface? And this is, in order to respond to this question, we need to go and talk about the electromagnetic spectrum that you can see on my slide. And basically, we are looking at the radiation that comes from a very specific part of the electromagnetic spectrum that is represented by the visible, the near infrared, and the short-wave infrared. This is the more traditional approach to try to detect materials by different properties that they have, but this can also extend to the mid and long wave infrared regions of the electromagnetic spectrum. Just because we're talking today about satellite remote sensing, I'm just gonna focus on visible near infrared and short wave infrared. And what we do here is that we discriminate between minerals based on their unique spectral signatures. So you can see here, I have an image of the ground, and this is what we call a hyperspectral data cube, where you see the surface of the ground, but then you see a lot of layers down below, and those are all the bands of information that we get with satellite data. So the minerals that are exposed at the ground, they exhibit diagnostic features that respond in the visible near infrared and the short wave spectrum. And the satellites that we have, they detect the reflected sunlight from these surfaces and record characteristic spectral signatures that we can use to detect and identify minerals that are in outcrops, in soils, and in the bare ground. So if we do a little zoom, we see that in each one of these spectral images, the information that is captured in each pixel is basically a spectrum that is a response combined of all the materials that are present in that pixel. And how we use this information? Well, we use the spectrum that we get from all the pixels in our image, and we compare with libraries. So every mineral has a spectral signature that is like a fingerprint. And as you see on the right side of my slide, I have some examples from a well-known spectral library from the USGS. So we look at the spectra that we can measure with our sensor, and then we compare with the unique signature of all the minerals that we expect that could appear in that area. So that's generally using some kind of spectral matching. So we try to match the spectra with the spectra from a library. And okay, we can detect minerals on the ground. And then why is this important? And why it is important for mineral exploration? The important part here is that these minerals have a response that can help us delineate alteration zones. So they might indicate the presence of mineral deposits or lithological boundaries that distinguish different rock types. So on the right side here, I have a very nice compilation from 2022, where they show the different geometrical patterns that some alteration minerals can show in a cross-section for porphyry, copper, gold, and moly mineralization and for epithermal mineralization. So in the different colors, you see different minerals. And on the right side of the diagram, we have the modified diagram of Corbett and Leach from 1998, highlighting all the minerals that we can detect with the spectral mineralogy. So different colors represent different mineral groups that we can see on the left side where they should be located. And the idea is that using this spectral mineralogy tool, we can kind of vectorize and try to find where is the buried mineralization. What is really important to notice here is that this is a surface method. So every kind of other material that is on the top of the ground will affect the spectral response. So if we have vegetation, dry vegetation as well, clouds, shadows, snow, etc., they will basically affect the kind of interpretation that we can do. Why we use satellite remote sensing applications for mineral exploration? This is basically because it's a very good tool for fieldwork planning and enhance the efficiency, cost effectiveness, and reduce the uncertainty of exploration campaigns. The first one is that it has a low cost for large areas. So satellite imagery is relatively cheap compared to the traditional fieldwork. So a single dataset can cover thousands of square meters for a fraction of the cost of sending stuff to the ground. Another benefit is that in the area of environmental and social impact by reducing the impact that we could have in exploration. So avoid clearing vegetation for land access and also limit the number of permissions that we ask. So basically, we're trying to better delineate the areas that we actually want to visit before having to visit more areas that may not be of interest at the end. Another one is to reduce the risk. So exploration can involve very harsh, remote, and politically sensitive areas. With satellite data, of course, we can assess the terrain before deploying, reducing the unnecessary exposure to hazards. And finally, another benefit of this technique is faster planning. So planning exploration campaigns, many of you know that they can include hiring equipment and setting up exploration camps, which can take weeks or months to organize. So satellite data helps pinpoint areas worth visiting, saving time and reducing logistical complexity. So those are some of the benefits of using remote sensing for mineral exploration. So we propose a workflow for mineral exploration. We have different sensors that work at different resolutions. So I think this is also important to set where we can use this tool according to the stage of the project that we're working in. So first, we think about a low resolution prospection. So generally, if we're working at the stage of project generation, for example, we want to identify relevant features across large areas. We want to identify where is the outcrop and assess the vegetation cover, for example. So this is a very good opportunity to use one of these techniques that can be lower cost. And here it is important to talk about the spatial resolution, and that's what I bring to the table now. So the spatial resolution is defined as the ground area represented by a single pixel in the image. It defines the level of detail the sensor can capture or the smaller features on the surface that can be detected and mapped individually. So just an example for this, we can see here, I have the images over an area in Western Australia. So on the left side, we have an image from the satellite WorldView 3. And on the right side, we have an image from Aster. So you can see that at the scale that we're looking at, we start seeing some kind of difference in the detail of the features that we can observe in the ground. For many of the people, Aster at this point can be a very good tool, because they can detect the areas where they're interested and then can go and select at a better resolution afterward. So then if we zoom in, we start to see the differences. So we zoom a little bit and then we start to see that WorldView 3 has a better resolution. So WorldView 3 is the multispectral sensor that has the best spatial resolution at the moment with 3.7 meter at shortwave infrared. So that's really an improvement from other sensors. And we see the difference with when we compare, for example, with Aster, which is 30 meters. And we zoom in a little bit more, we see that the level of detail that we can capture when we define that the spatial resolution is our objective. Like we really want to target specific features that are smaller. And that will also affect the quality of our interpretation because the pixels will be less mixed. So we will have less materials mixed in the pixel. So we can get an interpretation that has more confidence. And then once we did this first approach of low resolution, we go to the next step. So using tools like WorldView 3, for example, we start doing some kind of high resolution area selection for target definition. In this case, we can continue using multispectral or hyperspectral, but at increased spatial resolution. This will help us to refine geological interpretations, improve mineral mapping, and correlate the spectral signatures. So we want to define precise zones for fieldwork or drilling. And I just mentioned multispectral and hyperspectral, and I think that's important also to talk about. So here is where we talk about a spectral resolution. So basically, spectral resolution says how many bands we have in the image that we have collected. We could be working with an RGB image, so that's a typical photography that we use that only has 3 bands. But then we have multispectral, which collects data in 10 to 20 bands. And you can see on the middle of my slide the kind of a spectral cube that we can get with that. And just below that, we can see the spectra of different minerals and how they will look if we are capturing their signature using a multispectral sensor. On the right side, you will see the last data cube that is a hyperspectral image. That the difference that it has is that it has hundreds of bands and a very good bandwidth. So just below that, we can see how we see the spectra of the different minerals with a more detailed number of bands. If we go back to my example of WorldView 3 and Aster, so both are multispectral sensors and they have bands in the areas that can detect minerals that are very important for mineral exploration and specifically for the example that I just showed you before. And here we can see the difference in the spectrum. So this is basically the work that we do when we interpret the spectra. We grab the pixels, the information from each pixel, and by working with the multispectral spectrum or the hyperspectral spectrum, we compare with the lab measurements and give an idea of what we have on the ground. This is just a summary of an updated version of different sensors. So we see here the different wavelengths from 400 nanometers to around 12,000 nanometers. And then we see different sensors that in the areas that they cover. So I start with Aster, just next to the x-axis, and we see all the bands represented by these rectangles in different colors. So you see that Aster has all these bands. Then we see WorldView 3. We see the difference in the width of the different bands. I have also put Landsat, Sentinel-2, etc. And the important area that we work with is basically all the orange boxes. Those boxes are located in the areas where minerals that are important for exploration have a response. So by having individual bands that can detect those mineral changes will help us define them. Just on top, I just added ENMAP, so that's a hyperspectral satellite, some airborne satellite, and I also added some core scanners like HiLogger that can go just through the thermal, and then TerraSpec, just for a comparison of bandwidths and how we cover the electromagnetic spectrum. And I think this brings me to my last slide. So ground truthing and integrating spectral mineralogy. So in this slide, I just wanted to say that the interpretation that we do from remote sensing is always dynamic. So the idea is that we can validate and calibrate the spectral interpretation using field-based data. So how we do it, basically we can create a predictive map of minerals, and then we can use the spectral data from hand samples, soils, and regolith to improve dust definition. We can use field spectrometers, and also we can link later with follow-up drilling, maybe looking at what are the assemblages that we find even in core when we scan them, or we use portable spectrometer. And this is because there are limitations to this technology, as many technologies have. So we have mixed spectral signals that depends on the size of the pixel. We have different libraries, maybe not be appropriate for your project. And there are, of course, sensor limitations. So we work with different sensors, and each sensor has a better application. Just to finish up, I just wanted to show you two examples. So this is the spectral mapping of surface mineralogy over Marble Bar in Western Australia. So what we do here is to interpret and see which are the minerals that are present in the surface. So we can do this, as I mentioned, rock outcrops, soils, and regolith. And we can create maps basically looking at the probability of occurrence of the different minerals. And I just added here just a layer. So this is the way that I like to work with this data. So this basically shows me where is more probable that I will find a pixel that have a spectral signature of muscovite in this case. And this is quantitative information that we can use. We can integrate with other layers. We can use geophysics, geochemistry, structural mapping, etc. And it will help you improve your models, and also it will reduce the uncertainty that you have in the different areas. The last one is another application, but this is using a hyperspectral satellite over the Andes region. So on the left-hand side, you can see a mosaic of these images just in the border between Argentina and Chile. And what I did here was unsupervised classification. So basically, what you see on the right side is a false color composite of data reduction using the hyperspectral dataset. So these different colors here, they highlight different alteration minerals. So in red, in this case, we have high temperature alteration mineralogy. We have carbonate-rich compositions in cyan, lower temperature clays in light green, and iron-rich compositions in light pink. So this is another way that we can work with the data and many times reduce the uncertainty of the mineral interpretation. All right, I'm gonna give the time now to Essex to continue.
Thanks very much, Rocio. That was great, and excellent information there. And good afternoon, everyone. Thank you for taking the time to learn about how Geoimage can support your mineral exploration and mining projects. My name is Essex, and I'm an account manager here, and I'm excited to share how Geoimage, with 37 years of experience in satellite imagery and analysis, can tailor high-quality solutions to meet your exploration needs. Simply, basically, reach out and tell us about your project or problem, and we'll work with you to find the best path forward. Let's dive into some of the things that we offer, starting with data. At Geoimage, we provide access to a wide range of satellite data and commercial sensors to freely available sources like ASTER, Worldview 3, Hyperspectral satellites, Nmap, and Landsat. For commercial data, factors like sensor type, priority capture, and the size of your area interests can influence pricing, along with the nature of the AOI as well. We're very happy, for instance, if you had a large AOI with some areas you wanted to have a look at, we can do the interpretation in those particular areas, whereas to leave out the areas that you're less interested in, for instance, for cost efficiencies. We understand that every project is unique, so we help to select the right data for your goals. For free data sources, we go the extra mile to ensure quality. This involves assessing available captures, selecting the best options for your needs, and factoring in the working hours required to access and prepare the data, and for getting the most out of the analysis of said data. Our goal is to ensure that you get reliable, fit-for-purpose data every time. Now, let's talk about data processing. The size of your AOI and image resolution directly impact the time and effort required or needed for processing. Whether you're working with high resolution imagery or larger regional data sets, we optimize our workflows to deliver results efficiently. Our team uses advanced tools and techniques to process data quickly while maintaining the highest standards of accuracy. A critical step in our process is data validation. This is especially important when working with 3 sensors where data quality can vary. We rigorously assess the data, ensure its suitability for your project's purpose by catching potential issues early, like inconsistencies or limitations in the data. And I saw a question there about vegetation, which Rocio will get to. For instance, dense vegetation or vegetation, which does have issues, which I'm sure Rocio will get to in the questions part. At Geoimage, our mission is to support your project outcomes. Whether you're exploring a new site or optimizing an existing operation or tackling a specific challenge, we're here to help. Our team is passionate about finding the right solutions for you, and we take pride in our ability to deliver high quality results that make a difference. So how can you get started? It's simple. Reach out to us through our sales inbox at sales@geoimage.com.au, or you can also contact me directly. My mobile's on the page, and we're always happy to discuss your project or explore options and determine if our products and services are the right fit for your exploration needs. And all this information is, of course, available on our website at www.geoimage.com.au. Here's a breakdown of some of the satellites that Rocio was talking about and some of the SWIR-related satellites that we use. As Mark mentioned, we have a number of providers we use, but the ones that are useful for SWIR are more limited. Most of them are for imagery or radar purposes, but there's also yes, we'll get to the exciting part, which is the spectral interpretation. You can see this is where Rocio's expertise truly shines. Depending on the level of detail you need, we offer a wide range of workflows to suit your project, and we account for challenging conditions such as shadows or vegetation that can lead to false positives or whatnot. And yeah, whatever your project demands, we tailor our approach to deliver results you can trust. And in addition to satellite data, we leverage open access geological data sets to enhance our interpretations. These data sets can provide valuable context and support, helping us build a more comprehensive picture of your project area. But we don't stop there. If you have your own auxiliary data sets, such as geophysics, geochemistry, mineralogy, ground sampling, we can actually integrate them into our analysis to create a superior product. And we're very happy to get as much information as we can to make the most detailed spectral report as we can. So the more information we can get and utilize, obviously the better the chance the end product is going to be superior. Before I wrap up, just let me leave you with this. Geoimage, we're not just providing data or analysis, we're partnering with you to unlock the full potential of your projects. And with our multidisciplinary team and commitment to quality, we're here to help you achieve your goals. Whether you need a quick solution or a deep dive into a complex problem, we've got you covered. And I look forward to connecting with you and answering any questions and just exploring how we can help any of you with any of your next projects. Thank you. I'll pass it back to Mark.
Thanks for that, Essex. It sounded a little bit like a word from our sponsor, but that's us. So thanks for that. That's good. First webinar. And thanks for Rocio as well for that in-depth discussion. Rocio actually gave that presentation last night at 10 p.m. local time to some interested people in Chile, and it was all in Spanish. And I have to say, Rocio, it actually does make a lot more sense when I hear it in English today. So thank you for that. Okay, so Rocio has talked about, I guess, the current state of the technology. There's a few satellites, as you can see, that we're partnered with. I think the general trend, as it is in most of the satellite world, is towards smaller satellites, which is driven by cheaper launch costs and the ability to miniaturize the technology, which enhances the actual capabilities. There is a bit of a trade-off with that, though, and it's usually comes down to the size of the aperture that can be deployed, launched still, and how that impacts on the signal-to-noise ratio. So that's always something that we're looking very carefully at whenever we look to partner with a new satellite partner, and in terms of the data that they can produce for us. So we are eagerly awaiting the first imagery from our partner Pixel, they've launched earlier this year. We do have some imagery captured over WA for mineral exploration purposes, and we're expecting that to drop into our laps hopefully any day soon, maybe the next week or two. We'll keep our fingers crossed, but it has been captured, just going through the final QC for that. We also use Wyvern, which is another provider. Now, what are we looking at in terms of the future of hyperspectral or multispectral? And in some regards, what is the difference between multispectral and hyperspectral? We kind of hear these terms bantered around, sometimes interchangeably. The purists would say the hyperspectral needs to have many hundreds of channels and many hundreds of bands. But from a practical perspective, I think, as an explorationist, whatever gets the job done. So if you've got the bands that you need to identify the mineral assemblies that you're interested in then that, for me, that's job done. Do you really need 2000 if you don't need 2000? So as long as you can differentiate the minerals that you're looking for from the contextual mineralogy, then I think that's the right way to go. But that's my personal opinion. Now, one of the big challenges that we have that I see is there is a trend, I think, to try and increase the number of bands that are captured. That is still quite a high signal to noise ratio, because if that signal to noise ratio falls, then basically you're just collecting noise. You can't really do much with noise. It's pretty much rubbish in, rubbish out scenario. The swath width, so it's typically around between 10 and 20 kilometers is pretty standard now for the hyperspectral satellites that we have circling the Earth. Number of bands, so obviously WorldView 3 has got 16 bands, 8 of those are SWIR, and that's the sweet spot, as Rossio said, in terms of mineral exploration. We've got Wyvern, which I think has about 25 to 35 bands. Pixel has about 135 bands, but captures in 45 band subsets, and those bands are tuned for particular applications. So you've got either a subset that you could use for mineral exploration versus vegetation classification, etc., etc. And then if you wanted to, you could actually custom select particular bands if you wanted to. I did have a conversation with some people in the US in the last 2 or 3 months. They have very ambitious goals of building a sensor which they're calling ultra spectral, and I think they said 2,500 bands, and I think the resolution was 1 meter ground resolution, plus video, plus a whole bunch of other things too, which I like. I think that's incredible. I mean, if that can be achieved, that would be amazing. What I see the main challenge, though, not just in terms of that particular project, but any of these projects, is the data collection. Because if you recall, these satellites are pretty much flying computers, and so they store the data as they collect it. They get to a certain point, they download it through telemetry to a ground segment or ground station at some point on the planet, and then it gets processed at that point and then distributed to some other processing hub, and then finally makes its way to someone like Geoimage, where we do some more processing, etc. Yeah, so there is a finite amount of storage on board each of these satellite sensors. And so when we go into the hyperspectral, instead of using RGB and maybe the NIR, or maybe you've got 6 bands, when you start talking hundreds of bands, even thousands of bands, the amount of data you're collecting per capture is increasing exponentially. And so I see that as the tyranny of data, and that's something that the technologists will for sure need to be looking at in the future. So kind of watch this space in terms of, where we go from here. I guess my question out to the audience, to all of you guys listening in, is like, what would be the ideal spatial resolution for you? I mean, what would be the highest resolution that you would actually need if you were looking for mineral exploration? We've got 3.7 meters of SWIR with WorldView 3, and that's the highest that we can get in terms of spatial resolution. Does anybody really need 2 meter or 1 meter? So would be interested to see your thoughts on that one. So one possibility in terms of this tyranny of data, one solution, and there are some people working on this, is edge computing. Some of you might have heard of edge computing in other aspects of society. Certainly there are people working on edge computing in the satellite industry as well. So basically, what does that mean? It means you've got a computer on board that not just stores the data, but can actually process the data. And why would you do that? Exactly because you wanted to reduce the amount of storage, or increase your capacity to capture more imagery. So basically, and I haven't heard anyone say this yet, but I guess with AI, it's inevitable that you will be having some kind of processor control where you can select the bands in real time or near real time as you pass over an area of interest. And those bands would be specific to what you're particularly looking for in terms of mineralogy. The capture is then pre-processed on board the computer. The classification is applied, and then all you're basically downloading is the map. The old, the proverbial X marks the spot. If only it could be that simple. But yeah, but so that is one possible, I guess, evolution of the satellite technology. But let's see what happens. So that's a little bit about that, and my personal thoughts on emerging technology and a response to one particular challenge that the industry is facing. Would like to remind people that there is the Q&A that is open, so please, I know there's a couple of questions there, please put your questions through, and maybe I have a quick shout out to the two people who have joined us just because they're killing time. So welcome to you guys, and hopefully it's been entertaining for you, and maybe you've learned something that you can apply in your daily life. Jaden, do we have any questions there?
Yeah, we do.
Okay, so the question is, are we any closer to reducing false anomalies associated with vegetation?
Yeah, that's a very challenging one, especially because it's not only green vegetation that will affect your pixel. So generally, we recommend that if you see vegetation around the area that you're working in and you don't see outcrop, basically it's really difficult to separate if we have big pixels to separate the vegetation from the outcrop. So for example, dry vegetation that sometimes we see as bare ground, maybe when we look at an image, when we're looking on Google Earth, for example, just to assess if this would be a good technology. We see that dry vegetation has a peak in the 2,200 nanometer region. And that region is really important because that's basically the area where we can detect all the clay minerals that are related with aluminum OH. So those are the minerals that will indicate, for example, where are we located in that cross-section that I show. So if we have any kind of presence of that vegetation in the area, that will effectively affect that signature, and we will obliterate any kind of absorption feature that we had that was related to the mineral that was on the ground. So I think it's something that is there. It's very difficult to correct. One of the best allies for that is the spatial resolution. So if we can get better definition in the area and we can try to isolate all the pixels that have vegetation and try to minimize the number of pixels that have mix, like vegetation and outcrop, and that's basically one of the options that we have. So trying to get better spatial resolution. And in terms of the interpretation and basically when I work with data, if I have that kind of problem, I think I would apply a bit more strict interpretation. So when I do any kind of spectral matching, the algorithms that I will use, I will make sure that I can apply some kind of filters and threshold to make sure that the pixels where I have that vegetation, I should also have those absorption features that represent minerals. So it's not simple. And I think that is one of the biggest challenges that we can observe in areas such as Australia as well. Not so much in Western Australia, but maybe some things around this area.
Oh, fantastic. We have another question. Have you explored synthetic aperture radar data in mineral exploration? SAR data in mineral exploration?
Yeah, that's a great question. We haven't done that. It's not something I think that is in the mainstream. I mean, SAR offers a lot of advantages, that's for sure, and we do use SAR for other things. I haven't used it for mineral exploration, but I guess you could maybe use it in combination with some other satellite or other technologies. I guess you'd be looking at maybe some kind of correlation with the conductivity of the ground and the texture of the ground that has some correlation with the mineralogy that you were looking for. So it's possible that it could work in certain circumstances. I guess, like all of these things, as a geophysicist, there's no magic bullet that solves every scenario. It's more a case of looking at the tools in the toolkit and using what you have, and then a lot of inference that goes into that final decision-making process. So I would be interested. In fact, you've got me intrigued now, because I might actually do some research and see if we can find anyone that is using SAR for that. I don't know of anyone off the top of my head. There might be someone else in the audience that knows of some people doing some work in that area, but would be an interesting one to look at, that's for sure. Yeah, probably. So yeah, so we've got a response there from Amin. So yeah, so maybe we can connect those people afterwards, and they can have a follow-up discussion. But Amin, I'll probably talk to you about this as well, because it does sound interesting. Any other questions? No? Okay, that's good. We're probably running a little bit ahead of time, which is kind of nice. So I think in terms of wrapping up, hopefully everyone's got something from today's webinar. We'd be very keen to get some feedback from everybody and anybody in terms of whether you thought the content was too low level, too high level. You know, did you actually get some valuable information from it? Would you like us to talk about some other things in future webinars? I alluded at the start that super resolution, or the use of AI to enhance satellite imagery, is a bit of a hot topic, at least from our perspective, and that might be something of interest for people out there. There is some challenges with that, but if you're interested, let us know, and we can definitely do a deep dive into that one, the pros and cons of using super resolution, if you like. I think this is recorded. It's definitely recorded. I don't think that is definitely recorded, and we will put this recording onto the Geoimage YouTube channel. So feel free to go back. I think there was a lot of content that Rossio had in there. So certainly maybe worthwhile going back to that, or if you've got any friends or family that happen to be interested in applying satellite imagery to mineral exploration, and be sure to pass them on to that YouTube channel. I think that's probably be about it for us. Yeah.
I think we might, we'll wrap it up there.
So again, thanks everybody for your time. Thanks for your attention, and yeah, keep tuned. I guess one last thing, we are planning a world tour for Rossio. So we'll probably be heading over to the Western Empire, otherwise known as Perth, I think maybe in the next few weeks. So if you are interested in knowing a bit more about how to apply multispectral or hyperspectral to mineral exploration, and you'd like an in-person conversation with Rossio, please let us know, and we can definitely knock on your door and come and talk with you. So that may be, I'm thinking maybe the first week in November, around that time frame. Okay, thanks everybody.